Welcome back. In the last lecture, we have discussed on the experimentally observed intensity spectrum of blackbody radiation. And we have seen that the intensity of radiation increases with decreasing wavelength, attains its value, maximum value at a certain wavelength, and then decreases with decreasing wavelength. Now, this particular nature of this intensity of radiation for black bodies could not be explained by the existing science and technology. So there are so many attempts to theoretically predict this intensity spectrum. In fact, people tried to estimate the value of the intensity of radiation for different values of wavelength and frequency. And for that, a formula of intensity of radiation as a function of wavelength or frequency is required. And there are several attempts. And out of all these failure attempts, the important the attempts were given by Wien's radiation law, and by Rayleigh and Jeans, called the Rayleigh-Jeans formula. According to Wien's radiation formula, the intensity of radiation can be expressed in terms of two terms, where A and B are the two constants, and the two variables are wavelength lambda and temperature T. Now, it was assumed that the first part, that is A by lambda to the power 5, would take care of the intensity for lower wavelength region, that is for this region, whereas the exponentially decaying portion, that is e to the power minus b by lambda t, would take care of the intensity spectra for higher wavelength region. Now, if we estimate the value of intensity for different wavelengths and plot it, we will observe that for the lower wavelength region, the theoretically predicted value fit well with the experimental curve. But for the higher wavelength region, the theoretically predicted intensity values are quite different from the experimentally observed values. That means Wien's radiation law is very well for the lower or shorter wavelength side, but for the higher wavelength side, it is completely failure. The next attempt was given by Rayleigh and Jeans, called the Rayleigh-Jeans formula, which was derived from the classical concept. Remember that Wien's radiation law was not a derivation, it was just an empirical formula to fit the experimental curve. On the other hand, Rayleigh-Jeans formula was theoretically derived from the classical concept. And the intensity spectrum, according to Rayleigh-Jeans, is proportional to the temperature and inversely proportional to fourth power of wavelength. And if we try to estimate the intensity for different wavelengths and try to plot it, it will look like this, that in the higher wavelength region, the estimated intensities from Rayleigh-Jeans formula fit well with the experimental curve. But as we go towards the shorter wavelength side, then there is a large discrepancy, because as the formula predicts, the wavelength decreases, intensity continuously increases. Whereas the experimental observation says that after attaining a particular value of wavelength, the intensity should decrease. Intensity should decrease. But according to Rayleigh-Jeans, if wavelength is decreased towards zero, intensity of radiation goes towards infinity. So this large discrepancy between the Rayleigh-Jeans formula and the experimental result in the shorter wavelength region is called ultraviolet catastrophe. This large discrepancy is called ultraviolet catastrophe. Therefore, neither Wien's radiation law nor Rayleigh-Jeans law could explain the experimentally observed blackbody radiation curves. Though Rayleigh's law was good at predicting the intensity values at higher wavelength side, and Wien's radiation law was good at predicting the intensity values at lower wavelength side. After so many failure attempts to explain the experimental blackbody radiation curves, Max Planck of Germany came into rescue with his bold assumptions. According to Max Planck, the particles at the inner wall of any black body, the particles at the inner wall of any black body behave like simple harmonic oscillators. That is, these particles vibrate about their mean position simple harmonically. And energy the energy of those oscillators was considered to be discrete in nature. That was the bold move by Planck. The existing classical science says that energy is always continuous. That means that means if we want to increase energy from say 1 electron volt to 5 electron volt, then the energy can be increased at any step. It's just like a inclined plane. On that inclined plane, you can stand at any position you choose. So between 1 electron volt and 5 electron volt, you can have any amount of energy. Like you can have 1.43 electron volt, you can have 2.574 electron volt, you can have 4.935 electron volt. Any value of energy is possible according to the classical concept. Now, it was Planck who completely discarded this existing classical concept. According to Planck, energy is not continuous. The energy of the oscillators cannot be regarded as continuous. Rather, energy is discrete, energy is quantized. You can increase the energy by certain values only. That means if we want to increase energy from 1 electron volt to 5 electron volt, say, then we can increase it by certain steps. It's just like a stair. Now we are increasing the energy from say 1 electron volt to 5 electron volt with the help of certain steps, and the step size, this step size is constant. And according to Max Planck, this step size is h nu. H is called Planck's constant, and nu is the frequency with which the oscillators is oscillating about its mean position. Now, if you think of a staircase, you can stand only on those stairs. You can stand only on those stairs, but you cannot stand in between the two stairs. That means, in terms of energy, you cannot have any amount of energy. You only have certain values of energy. So if we say this is zero energy, then this one would be h nu amount of energy, because as Planck has assumed that the step size, this change in energy, the smallest possible change in energy could be h nu. So this will be 2h nu, this will be 3h nu, and so on. So in general, for nth energy level, we can say the energy En is nh nu. N can be 0, 1, 2, 3, any integer value, including 0. Therefore, in 1900, Max Planck came with his bold postulates regarding the nature of the linear harmonic oscillators of the blackbody. According to him, an oscillator having given frequency can have energies which are discrete. That is, energies can only be expressed as an integral multiple of finite quantum number with energy h nu, where h is the Planck's constant and nu is the frequency of the oscillator. This statement is called Planck's quantum hypothesis, and the quantity h, the Planck's constant, is 6.626 into 10 to the power minus 34 joule second. So according to Planck's hypothesis, energy is quantized, energy is discrete, energy cannot be regarded as continuous, and that was the very, very bold step. In fact, no one at the time believed Planck's hypothesis that energy could be quantized. But when this hypothesis, when this concept was utilized to find out the intensity or energy density of blackbody radiation, then it was a complete successful. Now let's try to derive Planck's radiation formula. So our objective is to find out the energy or energy density or intensity of radiation. Now for that, what we require, we need to know that there are particles at the inner wall of the blackbody which behave as simple harmonic oscillators vibrating with different types of frequencies. Now we are interested only those oscillators which are vibrating with frequencies between nu to nu plus dnu. That means when the frequency is changed by a small amount dnu, we want the oscillators which have frequency in between this range. Now, according to Planck's hypothesis, when the oscillators have some defined frequencies, they have defined energy levels. So, according to Planck's hypothesis, for any energy level n, the energy is nh nu. So, oscillators may have different energies, like say these are the different energy values of those oscillators. When n equals to 0, then energy is E naught, which will be 0. When energy is E1, then it will be h nu, E2, 2h nu, energy 3h nu, and so on. So for different oscillators, we have different amount of energies. So these are, so in general, if we have an nth energy level, the energy is nh nu. Now, there will be different number of oscillators in different energy levels. Suppose there are certain number of oscillators in this energy level, there are some oscillators here, there are some here, there are some, and so on. Now, if we want to find out the total energy of all these oscillators, if we want the total energy of all these oscillators, what we require first is to find out the number of oscillators in any particular energy level. That means we want to know how many oscillators are present in energy E naught. We want to know the number of oscillators present in E1, and so on and so. And that number can be predicted from the Maxwell-Boltzmann distribution formula, which says that for an nth energy level, the number of oscillators per unit volume is equals to some constant e to the power minus energy of that level by kt, where k is Boltzmann constant, it's a constant value, and t is temperature in absolute scale. If I want the number of oscillators in the first energy level, say n equals to 0 level, then it will be n naught e to the power minus e naught by kt. Now, according to Planck's hypothesis, the energy of nth energy level is nh nu. So it will be Nn will be n naught e to the power minus nh nu by kt. So this is the number of oscillators per unit volume in a certain energy level. So if we want the total amount of energy for all these oscillators, if we want the total energy of all the oscillators, what we will do? We will first calculate the total energy. We will calculate the total energy for the first energy level. So there are n naught number of oscillators per unit volume, and each has energy E naught, therefore total energy n naught E naught. Similarly, N1 is the number of oscillators per unit volume in energy level E1, and energy of each is E1. So total energy N1 E1. And if we carry the same process, we can have the energy for all the energy levels. So total energy, we just add them. So this is the total energy of all the oscillators. Therefore, what will be the average energy of all the oscillators? We will divide it by total number. So N0, N1, N2, and so on. So that will be our average energy. So in terms of summation, we can write the denominator as Nn, where n varies from 0 to infinity, and the numerator can be written as Nn En, where again n equals to 0 to infinity. We can write the average energy of the oscillator as this, where Nn, that is the number of oscillators per unit volume present in nth energy level, can be given by Maxwell-Boltzmann distribution, and the energy of a given energy state can be given by Planck hypothesis as NH. So if we put the values of Nn, it will be N naught is the word NH nu by kT, and En as NH nu. N naught cancel out. Now, if we say that for simplicity, that e to the power minus h nu by kT as x, then for n equals to 0, the denominator will be, for n equals to 0, it will be e to the power 0 means 1. The denominator will be 1. And what about the numerator? If n equals to 0, numerator gives us 0. Next, n equals to 1. If n equals to 1, then according to numerator, e to the power minus h nu by kt, which is x. Numerator will be x only. And denominator will be x only. And numerator, it is nh nu, that is now h nu e to the power minus h nu by kt, which is h nu x, because we have assumed x is e to the power minus h nu by kt. So n equals to 1 gives numerator as h nu x. Now n equals to 2. N equals to 2. So in the denominator it will be e to the power minus twice h nu by kt, that is x square. And numerator it will be twice h nu e to the power minus twice h nu by kt, which is twice h nu x square. Similarly, third, for n equals to 3, it will be 3 h nu x cube, and so on. So if we take h nu x as common, then first quantity is 0, second quantity gives us 1, third quantity gives us twice of, if I take h nu x as common, then it will be 2x only. So then it will be 3x square, and so on. Now the quantity in the denominator can be written as 1 minus x to the power minus 1. Similarly, the numerator can be written as the product of h nu x and 1 minus x to the power minus 2. So with simplification, it comes out to be h nu by 1 minus x minus 1. And if we put the value of x, we get the average energy as h nu by e to the power h nu by kt minus 1. So this is our average energy, when the assumption is that energy values are discrete in nature. If we try to estimate the same, that is, if we try to estimate this average energy from the classical concept, then that means when energy is regarded as continuous, then this value would come out to be kT. Okay, so average energy is estimated. Now we need the energy or intensity or energy density. So here we will first estimate the energy density of radiation. Energy density means amount of radiant energy per unit volume. For those oscillators having frequency between nu to nu plus dB. We are only interested of the oscillators having certain range of frequencies. Now, how will you estimate the energy density? So, what is energy density? Energy density means energy per unit volume. And to estimate it, we require two quantities. We require the number of oscillators per unit volume within this frequency range nu to nu plus d nu. We require number of oscillators per unit volume, and we require the average energy of each oscillator. Now, out of these two quantities, the average energy of the oscillator is already been estimated. Therefore, we only require this quantity in nu d nu, which is the number of oscillators per unit volume having frequency between nu to nu plus d nu. And from statistical mechanics, we have that quantity, we have that formula, and that is given by 8 pi nu square by c cube d nu. That is the number of oscillators per unit volume having frequency ranging between nu to nu plus d nu. So if we utilize these two, if we put those two values, then we get the value of energy density as nu d nu equals to this. Now, if we simplify it, it comes out to be 8 pi h nu cube by c cube 1 by to the power h nu by kt minus 1 d nu. So that is the expression of energy density, that is the amount of energy per unit volume corresponding to frequency range nu to nu plus d nu. So this was the Planck's radiation formula in terms of radiant energy density with frequency. And if we estimate the energy values in our intensity values or energy density values from this formula and put it or compare it with the experimental observed values, we will observe that these two values are completely matching with each other. That means the Planck's law is very, very successful in predicting the intensity values, in predicting the energy values, in predicting the energy density values for Blackbody radiations. Therefore, the bold assumption made by Planck is true. That is, energy must be discrete in nature. Energy cannot be regarded as continuous. Energy is quantized. Energy can be varied only by certain steps, and the smallest possible energy value could be h nu.